sorry. All right, so what we're going to get into today is some function work. Okay, take much. Do some function work. This is a lot of stuff that you guys already have a little bit of a background with. Kind of reiterate, the course is taking things that we have somewhat of an understanding for and dive into them a little bit deeper, maybe look at them in different perspectives. But throughout the entire course, guys, this is kind of a functions course. Okay, we talk about different types of functions throughout the entire thing. So when we first introduce a function, hopefully you realize you understand the importance of really getting a good understanding of it and being able to kind of use the notation that we're going to describe today. Okay, a function is a relation in which each possible input value leads to exactly one output value. Okay, each input leads to exactly one output. Okay, sometimes you might see a phrase that says something of the nature, for every x value, there is one and only one y value. Okay, that's another way of stating what we're talking about for a function. Okay, everything we've done algebraically, when you guys get a equation, it's a relationship. Okay, that's all we mean by relation. It's taking a set of values and showing you how they relate to one another. What's the link between them? Okay, there are different groupings of relations. Okay, some relations are functions, some are not. Okay, y equals x squared is a function. It's a relationship between x's and y's that produces what we call a function. The equation x equals y squared is still a relation. It still takes x's and y's and compares them to one another, but it's not a function. Okay, so the relations is kind of the overall kind of grouping of objects and how they are comparable to one another. But inside that, then we have like kind of separate categories. Okay, we have things that are functions, things that are not functions. Okay, and then when we have functions, we'll have, okay, this is a polynomial function, this is a rational function, this is a logarithmic function or an exponential function. So we have kind of branches that go down from that category. Does that kind of make sense? But the key to being a function is that for every x value or for every input value, there is one and only one output value or y value. Okay? We say the output is a function of the input. Okay? There's a lot of things in real life that we use to model with functions. Okay? So real life phenomena that model that are modeled by functions. Last class we talked about your height. Your height is a function of how old you are, isn't it? Or a function of time. When you're small, when you're young, you're small. Okay, so a small time value gives you a small height. A larger time value makes or produces a larger height, right? Does that kind of make sense? And at some point, you're going to reach your maximum height, correct? Okay, and then eventually, as you get older and older, you start to shrink a little bit, don't you? Okay, so height is a function of time. If I think about like miles per gallon in my car, okay, I get 15 miles to gallon, I get 30 miles to gallon or something like that. That's a function of how fast I go, okay, or a function of my average speed. You guys have all seen commercials that says this car gets 35 miles per gallon in the city, right? Or 40 miles per gallon on the highway. Well, if you read the fine print, it says they're on the highway, but they're going 45 miles per hour. Okay, because the optimized value, okay, the largest miles per gallon is obtained by driving a reasonable speed. If I go really, really slow, I'm wasting a lot of gas. I'm not getting very far. If I go really, really, really fast, I'm getting real far, but I'm using a lot. Or sorry, really, really fast. I'm going real far, but I'm using a lot of gas. Does that make sense? So that means I get little miles per gallon. But if I'm somewhere in a reasonable speed, I will maximize my potential for my gas. There's a lot of different things throughout real life that we can model with functions, okay? And we will do that, if I take think about like chemistry or science or something like that, take a boiling water. The temperature of that boiling water is a function of the time that it is been off the burner, right? That kind of make sense? Okay. Maybe you've done that experiment in chemistry or maybe not experienced in grade here where you start taking temperatures of things, right? Take temperatures of hot water. Did you guys do that? It's kind of a basic chemistry process, right? And then you plot that data and then find the line of best fit, and that line of best fit then could be an algebraic representation of the temperature from some time. Okay. All right. So the input values, those are what we call our domain values. Inputs are our domains. Inputs are our x values, or inputs are referred to as our independent variable. Okay. So we got 4 things that we can refer to our input value as. Okay. And that's going to provide us our output value. We call our output value our range. Okay? Our output value or our range value is the dependent variable. Okay? A lot of times you will think about it as your y value. Okay? So I'm going to write these things down for you. I think it's a good idea to kind of pay attention and look at, because what happens is a lot of people get confused and they flip-flop domain and range. They flip-flop independent and dependent. So if we're talking about x's and y's, which one comes first, alphabetical, x or y? X. Okay? So x is first, y is second. Now, think about domain and range. Which one comes first, domain or range, alphabetical? Domain. All right, so we got domain with our x's in. Range with our y's. Okay? Now, this is a little bit different, okay? That's how I remember my domain and my range. And even you can go, input is alphabetical with, in comparison to output, right? Make that blue. So if you struggle with these things, understand that their structure, and it's not done on purpose, but the structure is kind of alphabetical, okay? Especially with domain and range. The one's different, not alphabetical. This is your independent variable. And this one's going to be your dependent variable. All right, if you understand what those words mean, independent, okay, I would probably venture to say most of you are not independent. Most of you probably rely on somebody else for shelter, for clothing, for food, that kind of thing. Okay? So you are dependent on somebody, right? Okay? I am independent. I'm the only person that I'm needing to support myself is myself. Okay? So I'm dependent. So if I think about my x's and y's, or my domains and my ranges, my domain is my x values. And in any relation, it's your x values, and they can be anything they want to be. They are independent. Nothing impacts them. Okay? But when I plug them into my rule, my algebraic rule, there's a rule that's going to kind of manipulate and change that value, and the output that I get, that value that I get as an output, is dependent on what I started with, what I plugged in. Does that kind of make sense? Okay? So think about like your height based off of time as a function of time. Your height depends on how old you are, right? Okay? The temperature of the day depends on what time it is of the day. Okay? So a lot of your functions we're going to think of them that way. All right? In regards to independent, dependent variables, inputs, outputs, ranges, and domains. Okay? All right, so different ways that we can represent functions. We can talk about them verbally. Okay? So kind of like what I was doing with your height being a function of time, that kind of stuff. We can do it numerically, okay, by a table. Sometimes we can do it visually by a graph. Okay, and there's and I'm not sure where we would put this. It's kind of like a table, but it's also kind of a graphical representation. But there's a mapping that we'll have. Okay, it's maybe a technique that's not listed there. The final way, which is the one that we like to use the most, is algebraically, by an explicit formula. Okay? By using variables and coefficients and stuff like that in our order of operations to express how our x's are related to our y's or vice versa. Is that okay with everybody? Okay. Before we go on, I need you to understand that to make a function, to have something being a function, this has to be true. So I'll give you an example of this. If I go y equals x squared, okay, this we can call a function, okay, because my input values, think about an input value of just like 5, okay. If I plug 5 in for x, what do I get back? 25. For that one x value, for that one input, I got one and only one output back, right? Meaning that if somebody else puts 5 in there, what are they going to get back? 25. And if somebody else puts 5 in, what are they going to get back? 25. No matter what you put in, and no matter how many times you do it, you keep putting that number back in over and over and over again, you'll never get something different than 25 back. Okay? So that means for every input, there is one and only one output. Every number on the real number line is going to do that for that function. Okay? If I do that, so it's x equals y squared. Okay? Now to make things maybe obvious here, let's solve this for y. Let's make this an explicit function, or explicit equation, I guess, solve for y. So it would look something like that, right? Okay? Now there is one value here that this would be a function. Okay? But I need all my x values to have this relationship for this thing to be a function, right? It could happen a million times to where it is a function, but one value, one x value not have this one output value relationship, and it would not then be a function, okay? So 0 does this. No matter what time, how many times you put 0 in, what are you going to get back? 0, okay? 0, 0 satisfies the condition for that input value has one and only one output value. I'll plug in 4. What do I get if I plug in 4? Plus or minus 2, right? I get 2 outcomes, 2 outputs for that one input. That violates the definition of a function, right? Does that make sense? Okay. So, you might be a person who says, I put 4 and I get 2 back. Put 4 and I get 2 back. Put 4 again, I get 2 back. But your neighbor says, I put 4 and I got negative 2 back. That's a problem. Okay? That violates the conditions for setting up a function. Alright? You guys remember the vertical line test? That thing would violate the vertical line test. The y equals x squared, you guys know that to be a parabola that opens upward, like such, right? Y squared equals x. That is a parabola that opens up to the right, if you remember conic sections from last year. Okay? The one on the left there passes the vertical line test, meaning that for every x value, we only intersect the vertical line once, producing only one output. The one on the right fails that. Okay? And we will define the vertical line test here in a little bit, probably tomorrow. Moving on then, so now we understand what the description of a function is, how we define it, how we think about it. Now we're going to talk about the notation for it, how we write it and use mathematical terms. Okay? So the notation y equals f of x defines a function named f. Okay? So y equals f of x. If we read that, what we're saying then is that our y, or output values, our range values, are going to be defined or created by some rule that is f of x. Okay? We read it as y is a function of x. Says the letter x represents the input value or the independent variable. The letter y, or f of x, because y is equal to f of x, represents the output value or the dependent variable. Okay? So f of x is going to be our notation for a function. Usually start with, if you haven't used a function or haven't used any letters, you usually start with f because of it being the word function starting with f. But you can use a of x, b of x, c of x, d of x, whatever. I'm talking about cost. Okay, cost is maybe a, a lot of times we talk about these three functions: cost, revenue and profit. Okay? Well, maybe X is the objects that I'm selling. Okay? So the cost might be a function of how many objects I've had to make. Revenue would be the money brought in by the number of objects that I've sold. And profit is then revenue minus cost. Okay? And we'll talk about these things down the road when we start seeing like specific examples of these concepts. But you see there that I don't have to use just F, right? I can use things that describe or letters that are indicative of the concept that I'm trying to portray with my function or my rule. Okay, so cost, revenue, profit, those types of things. We've already done a very useful function. You guys did this, right? Okay, that's the height. That's why we use H. Okay, at a particular time. Okay, so we can not only change the name of the function, but we can change the input variable to maybe be describing the type of input value we have. Is it a time? Is it a simple X value or something like that? Okay. All right. So the first way that they're going to ask us to work with functions and to evaluate them is through tabular form. Okay. The first thing I think is important to recognize, there will be times when they ask you, is this thing a function or not? Okay. Now, because we are going to ask questions A, B, C, and D, it is a function. But if it was just this table that said, is it a function or not, you have to go check against the definition of whether this violates the definition or not. Okay? The definition says for every input value, there is one and only one output, right? So I need to go look at my input values and see if any of them duplicate. Okay? Because if they duplicate, then there's a potential that there'd be a duplicate output, right? Well, do any of my X values duplicate? No. Okay? So automatically, if my X values don't duplicate, then there's no way that my Y values could duplicate for one X value. So this is a function. Okay? But if I had something look like this, maybe right here we rewrite this as -2, 7. Okay, so we add another value to our table. Now do any of my input values duplicate? Yes, -2 shows up twice, right? Now that doesn't mean right off the bat, because -2 shows up twice, that this isn't a function. We now have to compare the outputs. Are the outputs for both -2's different? Yes, that's the problem. Because I can say, everybody, what's the input of -2, or what's the output for -2? And half of you might say 5, the other half might say 7, right? That's the problem. That's the issue. We want to make sure that everybody says 5 is the output, or 7 is the output. We don't want people on different pages. Is that okay? If I put a 5 here, okay, even though my inputs duplicate, I have 2 -2's. Is the output the same for both those? Yeah, so it's the same data point twice, so that's still a function. Okay? For that one input of -2, I'm only getting one output. Okay? So the notation here, guys, when they say f of -4, okay, that -4, because our notation is f of x. So the -4, we're really not doing any algebra with that -4. For this particular problem, it's more of an identifier. Evaluate this relationship at -4. So I go find my x value of -4. Okay, so x value is -4. What is my output value? What's my range value that goes with that? F of -4 is 10, right? Okay. This is your x values are your what? Are they your domain or are they your range? Domain. And f of x are your range. Okay. So this is asking, what is the range value? What is your output for the domain value of -4? Okay. What about f of 0? What's that one? That's going to be 1. All right. The next one gets to the concept that with functions we can do all of our operations. We can add them, we can subtract them, we can multiply them, we can divide them. We can multiply by coefficients. We can We can square things because of multiplication, all that kind of stuff. Okay? But you have to kind of evaluate the functions first. So f of negative 2 would be what? 5. So f of negative 2 is 5. We then have plus. Now what's f of negative 8? 20. So what's that give me? 25. Okay? So all that says is that you can add the range values, or you can add the y values of two different graphs. Okay? Or two different data points. And that's hopefully pretty straightforward that if we can multiply them, or if we can add them, we can multiply them. We should be able to subtract them, we should be able to divide them. Okay? Now ask me what's f of 3. F of 3. Is 3 an input value? Okay, so 3 is not in my list of inputs, right? So it is not a defined input value. Okay, meaning that when I run it through my rule, I'm not allowed to, right? There is no definition for that value. So what's my output then? If my input's not defined, my output can't be defined either, right? Okay, and what happens there a lot of times, guys, is that we have the idea of, like, we saw this last week. Like, if that's my rule, that's my function, do we have a problem by plugging 3 in here? Yeah, okay. 3 is not defined for this function, so I plug it in there, 1 over 0. I don't know what that is. I don't have an output with that. It's an undefined output. Okay. Is that stuff that we've done before, feel comfortable with? Okay, good. So what happens a lot of times, guys, is they could give me the same thing, this table. They could give it to me as a set of ordered pairs, because really, if I go domain and range, domain, comma, range, is that the same thing as x, comma, y? Okay, now we're not using y values, we're using f of x values, right? But we said when we defined the notation for functions, we said y was equal to f of x, right? So if they could give me this list in this one, they could just say 0, 1, negative 2, 5, negative 4, 10, negative 6, 15, negative 8, 20. Okay? If they give it to me that way, it's the exact same idea. It's tabular form. A lot of times they call that like maybe roster notation with sets or whatever, but you can change it to a table real fast. Okay? And you can answer the same exact questions. If I ask you f of negative 4, well, I go find the order pair that has an x of negative 4, and then the y value of the f of x value then is the 10. Okay? You can change, every time that I give you a table, you can change it to ordered pairs. You can change it to a graph. Okay? No matter what representation I give you of the function, you can convert it into all the other representations. Okay? Some are easier than the others. Some are nicer to look at to make connections or statements about the function. And that's why we kind of learn all the different types of techniques, because some are maybe in some aspects a little bit more beneficial than others. All right, so here what we're asking. Okay, I want to look at these graphically first before we get into kind of evaluating them. But it says let f of x be equal to root x plus 1, and let g of x be equal to negative x squared plus 2. These are two functions. Okay? And now we understand the rule that makes that relationship, right? And the last one, in the table question, we didn't know what the rule was. Okay? And what you guys have maybe done in a science class is maybe you collected data points like we had in that last table. Maybe we go back to that question where, or that chemistry experiment where we're boiling water, and then we want to talk about how that boiling water is going to recede to room temperature. And we start taking measurements of it and recording temperature at certain times, right? But maybe we want to do that for like 5 minutes, 10 minutes, whatever. Okay? And that data plot might be kind of scattered a little bit, but it should show a linear effect, okay? A linear correlation between the data points. And then you guys then took and did the line of least regression, or line of best fit, right? And come up with an algebraic rule that models that data, okay? These are algebraic rules that are modeling data, okay? We're going to now say, okay, if these are the algebraic rules that are getting us our output values, what are those output values? Okay? Now understand what's going on. F of x equals root x plus 1. That's a curve. Okay? I think I've got it up here. Okay? So let me go back to standard view. Okay. So root of x plus 1 is that green curve. Okay? G of x equals the opposite of x squared plus 2 is that parabola. They are both functions. For every x value, each of those has one and only one y value. Okay? So they are functions that pass the vertical line test. But the questions are, what is f of 4 minus g of negative 2? Well, f of 4 means that I'm going to look at the f function. I'm going to look at an x value of 4 and see what y value is generated from that. Does that make sense? So algebraically, if I'm going to find f of 4, remember what this means. This means, if I were to put it right underneath here, f of 4, the x now became a 4, right? So over in my rule, the x becomes a 4. So what's f of 4 going to produce for me? 3. Okay? Then we'll try g of negative 2. So that means over here, I plug in negative 2 there for x. So that means over on the right-hand side of my rule, I get a negative 2. Now here's the only thing that you have to be cautious of. I'm taking negative 2 as my input. So that's the thing that gets squared. So negative 2 gets squared. What's negative 2 squared? 4. And then we take the opposite of that. What's the opposite of that? Negative 4. Then we add 2 to that and we get negative 2. Okay? So this was 3. This was negative 2. And now we're going to do what with them? Subtract them. What's 3 minus negative 2? Gets me 5. So that's the algebraic way of doing it. Let's look at it graphically. Okay? Graphically, we said we're going to plug in 4 to the f function. So let's see here. Let's just get the f function up there all by itself. I'm plugging 4 into it. Okay? So that means my x value is 4. If my x value is 4, what's the y value going to be? It's going to be there at 3, right? So you see the input, the domain value produces an output or a range value of 3. Is that right, everybody? Okay. If I look at g of x, we were trying to plug in negative 2. So if I look at the x value of negative 2, what's the y value that goes with that? Negative 2, right? Input of negative 2, output of negative 2. Okay? So now the question is, when I ask, because these are both, or this one I guess up top is, this one here is an x value evaluated at f of x. This one here is an x value evaluated at g of x. And what we did is we used specific x values of 4 and 2, but then didn't we just say subtract those? So you see how we're subtracting these y values? 3 minus negative 2 gave me 5, right? Because that's what was written down. It said f of x minus some g of x. But this x was 4 and this x was negative 2. Is that okay with everybody? All right, so you can look at these things graphically to describe them that way. Yes, ma'am?
How did you know to take the positive? Like, can it be negative?
Because, so if I have like some equation where we have to apply the square root. So let's say we have x squared is equal to like y plus 1 or something like that. And I want to solve for x. Then I have to understand that because I'm applying the square root, there is a plus or negative aspect, right? Because this started for us this way, this was generated for us, and there's nothing out front, that means they only want you to look at the positive version. If they wanted the other part, they would maybe give it to you as another function, or if they wanted the negative version of this, they would just put maybe the negative sign up there. So when it's provided for you, they're under the assumption, they're understanding that it's not plus or minus, it's whatever's there. Good question. All right, so this bottom, or sorry, b, I guess. Okay. We've got g of 3. Okay. So I'm going to come up to the g function, plug in 3. So we get negative, and it'll be 3 squared plus 2. So that's going to give me what? Negative 7. And then I'm going to go 2 times f of 1. Well, I've got to figure out what f of 1 is first, right? So evaluate, try to find f of 1. So it's going to be root 1 plus 1. What's root 1 plus 1? 2. So as we're doing these operations on these functions, evaluate every function where they're being asked to be evaluated at, and then plug those values down, or in down here. So g of 3 was negative 7, plus then 2 times f of 1. When we said f of 1 was 2, what's that going to end up giving me? It's negative 7 plus 4? Negative 3. Okay. Eventually, in the next couple of days, as we see more and more different methods and approaches, representations of functions, we will do the exact same thing graphically. Okay? We'll do the exact same thing in tabular form. We'll do the exact same thing using ordered pairs. Okay? You know, I could come back up to this up here and ask you, you know, what is, 2 times f of x? Okay? Maybe I do it this way, 2 times f of negative 2. Well, I find f of negative 2, right? That gives me 5. What's 2 times 5? 10, right? Okay? So we could do those types of things even in tabular form. You see down here, tomorrow we'll start class with doing one in graphical form. I'll leave C for you because we're kind of running out of time, but I want to do D, because D is one that people really struggle with. When we start just taking, and this is what we like to do a lot of times, okay? We like to, essentially, instead of our input being numerical, we like our input sometimes to be an expression. Sometimes we like our input to be another function, okay? And we have to be able to understand our order of operations to evaluate these, okay? So the first thing here is first evaluate f of b. Well, think about what we did last with like f of 2 and f of 3 and that kind of thing. It was pretty straightforward, is that we wrote underneath this like f of 2 or f of 3 or whatever, and we saw that x became 2 or 3, right? Well, now it's just b. So what's x going to turn into? Just b, right? So wherever I see an x, I replace it with b. Okay? Why is that beneficial? Well, somewhere down the road or somewhere maybe previously, we have defined b to maybe be some other object. Maybe b is being defined as the even values. Maybe 0, 2, 4, 6, 8, something like that. Is that going to make sense? Or maybe b has another rule. Maybe b is equal to x plus 1 or something like that. I don't know. Okay, but that's the benefit of being able to just take a variable input value and see what that output then looks like. Okay. Now the hard part in this question is g of a plus 1. It is now an expression that we're plugging in for x, right? Okay, a little bit more complex. So how do we address that? We put a negative in here, and now it's a plus 1 becomes our x, right? But now it's a binomial as the input. All right, we're going to square a binomial. What do we do if we square a binomial? We FOIL it, okay? So this negative stays here because order of operations says do exponents before you do any multiplication, right? So this negative 1 means we're going to multiply everything by negative 1. Well, I have to do the exponent first. So that's going to give me a squared plus 2a plus 1, right? Plus then 2 at the end. Now I can negate the a squared plus 2a plus 1. So it gives me negative a squared minus 2a minus 1 plus 2. Remember, I'm going to distribute that negative all the way through. So does that give you negative a squared minus 2a plus 1? Mm-hmm. Okay. So now I know what f of b looks like, and now I know what g of a plus 1 looks like. What can I do with those two things? Now I can do the order or the operations they asked us. We can add those together now. So I'm going to go negative a squared minus 2a plus 2 plus root b And that's my rule now for that sum of functions. I will post at some point today a function assignment. Will not be due for a couple days. Remember, there is still that absolute value assignment available online to work.